Okay folks, this rig here is, it's called the Dunkerly's rule experiment. But what we have here is a simply supported beam, and we have a unbalanced rotor motor in the middle, and we're going to use that to induce a force vibration. Now, there's an unbalance here. I'll show it in a second. Okay, so you see here this it's kind of a cam really. This rotates around, but you can see it's off center, so it's going to create a rotating imbalance basically and cause the beam to go up and down. Okay, so that's our setup. So what I'm going to show you is I will set the motor running, and we know what the RPM of the motor is. We convert that into hertz, so we know what the frequency of rotation of the disturbing imbalance is. And what we're going to do then see is resonance of the beam. In other words, we're going to get increased oscillations at the frequency, at its natural frequency. So we're going to do a demo of that in a minute. Our original mass here is 0.8 kgs. This is what's in the middle. And then we're going to add additional masses and increase the mass of the system. And as we increase the mass of the system, we get a reduction in vibration. Now, what we're going to use is a couple of methods for calculating the frequency. Number one, we're going to do it experimentally. Then we're going to use Dunkerly's rule, and we're going to use Raleigh's method as well, and see how those compare with experimental values. Okay, so we have the rotating imbalance at the moment. We're running at about 6.5 hertz. I know the frequency of oscillations of this is around about 9. So as I increase the frequency, we should see an increase in the response. Okay, and that's around 9.2 hertz. And if I go beyond that, it reduces down. Okay, come back down up to resonance, come back down to 9.2. And you can see a much greater response. Now I don't want to dwell at that resonant frequency because I don't want to break the thing, because it actually does theoretically want to, the amplitude goes to infinity. So now the next step we're going to do is add an additional mass and see what the renewed frequency is, and it should be reduced. Okay, we have added 2.1 kilograms onto this, so we have a mass of 1 kg in the middle in total, believe it or not. Yeah. No. By the way, Derek is doing the photography. Thanks very much, Derek. So we've 1 kg in the middle, so we increase the mass, so we should see a reduction in the natural frequency. From previous data, I'm expecting it to be around 8.4 hertz. So if I turn this on, and I'm just at about 7.6 hertz now, increase it, about 8 now, and you can see we're kind of getting resonance there, and that's 8.4. Okay, so that's pretty resonant. Now if I just go beyond it, it's to prove that 8.4 is actually the resonant frequency. 8.5 is still quite, and 8.7 it reduces down, okay? And when we hit 9, so you know, we're getting pretty rough and ready answers there. It's very much a visual approach to when we're getting resonance, and exactly when this resonance occurs, when the amplitude, and we're not actually measuring the amplitude, we're doing it by eye, but that's okay. It's around the value we think it is, okay? We can show, as long as we show that below it has a lower oscillation and above it has a lower oscillation, we're kind of extrapolating and saying it's roughly in between here. It's just a demonstration. So we're going to show you some sample data from previous experiments, and then we're going to look at doing the calculations and see how we get on.